Can you see any DNA? No. That's because DNA is actually soluble in water, okay? It's soluble. What does soluble mean? Yes, Tony?
It can dissolve.
It can be dissolved, yes. So what we have is the DNA which is dissolved in there, okay? Now, if I can show you what I've done earlier, just for clarity, here it is. Again, we still can't see the DNA, but the DNA is present in there. Now remember, remind me again, DNA is found as what? A double helix, okay? So DNA is a double helix strand. They're all found within there. Now, what I have here is some alcohol, very, very, very strong alcohol. Although DNA is soluble in water, it is insoluble in alcohol, insoluble. So what do you think I can do to get the DNA out of there? Yes, Sean.
You pour it into the alcohol.
Pour it into the alcohol, very, very good. Or I could pour the alcohol into the DNA. Yeah. Let's have a go at this. Sometimes this works, sometimes it doesn't. What we'll see are two separate layers. Yeah. In the second layer, hopefully, the DNA is going to separate out, and you will see it either as some fluffy white pillows, or hopefully some strands of DNA. Can you see any strands coming yet?
Yeah.
Can you? Yeah, look at that. All right, fantastic. Eugenia, can you get me a cocktail stick out of there for me, please, very quickly? Look at that. Can you see it?
Yeah.
That is actually real DNA, which has been extracted from these thymus glands. So what I'm going to try to do is pull it out. Here it comes. Can you see it all pulling out? It's a bit like snot. But it's far, far more important than that, because that in there contains all your genetic information. DNA. Okay, let's put that away. Where's the DNA held?
In the nucleus.
Fantastic. It's held within the nucleus. So can I have 3 volunteers, please? 1, 2, 3. Up you come. To go into the nucleus. And this time, the DNA code is not a color code. If you can stand in there, the DNA code is a letter code. If you can hold the clothesline for me, please. One over here, one in the middle. Patricia, do you want to come around to peg them on? Okay, using the previous model, we had a red, and what did we put on the first peg? Red. This time we have a C. So what would common sense say to put on there? Common sense would say to put on a C. However, it doesn't work like that. DNA is a double helix. It has complementary bases. Complementary meaning
things that go together.
Things that go together but are not exactly the same. Fantastic. So we're going to have to use complementary bases. So we're not going to use a C. What are we going to put up there? Does anybody know from the structure of DNA? Can anybody remember what the complementary base for C is? Yes, Eugenia?
G.
Fantastic. It is a G. Should we write that down as a rule, please? C goes with G. So it stands to reason that G is going to go with Eugenia.
Does it go to C?
Fantastic. G is going to go with C. C is going to go with G. They're complementary in the double helix. Do we understand that? So what will be the first one up?
G.
Okay, do you want to put on the first peg for me, please? On the first peg. We have a lot of pegs. Look what he's doing. Is he right?
You're putting a G to C. CC? Yeah.
Okay, so could you modify that for me then, please? Fantastic. Is he right now?
Yeah.
Okay, keep going. Go on, Tricia. What's the next one? C goes to... Fantastic. T is going to go to... A. Wonderful. Well done. So T goes to A. Can you just put the 2 A's on for me and stop there? Now, Laura, a second ago I said to you, if C goes to G, G would go for C, yes? Yeah. So if T goes to A, what does A go to?
T.
A goes to T. That makes perfect common sense. And that would be nice and easy and straightforward. Science is never easy or straightforward. I'm afraid we don't have any T's. We're going to have to substitute with a different letter. A always goes to U. Sorry. So, Trisha, A goes to U. Shall we write that rule down and underline it? Because that's a very important one. So, let's have Trisha out here. So, A goes to U. What's the next one? A goes to U. Martin, do you want to take up the slack on the line for me, please? Fantastic. So we're making a copy of the DNA. Now, remember we said the DNA is a double helix? For simplicity, what we've shown on the board is only one of those strands. Only one of the DNA strands is shown, okay? Because only one of the DNA strands is actually copied. Only one strand is copied. Now, this strand has a very special name. This copy of the DNA has a very special name. Does anybody know what it is? If you like, this strand is a messenger, isn't it? It's a messenger which copies it and takes it to the workshop. But of course, we haven't got a workshop in the cell. What we have is an area called a ribosome. Write that down for me, please. We have an area called the ribosome. On your model, where you've put workshop / ribosome, because the ribosome is a workshop, if you like, of the cell. Okay. Now this strand, which is coming along nicely, as I said, is a messenger. It is sending a message to the ribosome. Okay? So we call this strand messenger RNA, or mRNA for short. You might want to write that down. Messenger RNA, mRNA. Okay, we nearly done? I think that might be plenty. Okay, very, very carefully, let's take it over to our ribosome. So we leave, where are we leaving?
Nucleus.
The nucleus, fantastic. We're leaving the nucleus and we're going over to the ribosome. Here we are. And stand up nice and straight behind and hold it up for me, please. Make sure you don't lose any, because it's very important. Hold it up straight. There you go. Fabulous. So there is our mRNA strand at the ribosome. Is everybody with me so far? Yeah. Shall we walk through again? So, we go to the nucleus and we copy what?
The DNA.
Do we copy both strands?
One strand.
Just one strand of the DNA. And what is the copy called?
Complementary.
It's called?
Complementary code.
The complementary bases, excellent, form the what strand? What do we call it? mRNA. And then the mRNA leaves the nucleus. And where does it go to? The ribosome, which works as the what of the cell? The workshop where we construct things, okay? And the last time we used car parts. The ribosome does not use car parts. It uses something called amino acids, which are the building blocks of what? Proteins, fantastic. Proteins. So we have our amino acids. But this time, obviously in our body, we don't have a supplier. What we have is molecules called transfer RNAs. And what does transfer imply? What does transfer? If you transfer something, what does it imply? You switch, you move something, okay? You take something from there over to here. Now, what's missing from our model? What did we have last time? Here.
Someone to carry a supplier.
We had a builder. We also had a person who would decoder. So can I have a decoder here, please? And can I have a builder? A decoder? Yep. Do you want to come across? Now. Shh. Watch. It looks really bad, but it's not. Okay? Describe what you see to me. What do you see? Remy, what do you see there?
I see like
In each box.
I see in each box I see a code or something. Which one?
3 capitals.
Yeah, 3 capitals.
3 letters. A 3-letter code. Do you remember we had a 3-color code which corresponded to a part? Yes? We have a 3-letter code. What do you think that corresponds to? The mRNA code. So, let's say for instance, what's the first one, Zina?
GGA.
A. Find me GGA, please. Fantastic. Now the part that you need is written next to it. So what would be the part you need?
GLY.
GLY. Now GLY is short for glycine, okay? Which is the amino acid. Now, where did I say these are carried by? Who carries these? Transfer RNAs. Can I have 12 of you, please? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Could you come up and be transfer RNAs for me, please? Hold them high and proud above your head like so. Grab one each. Okay, hold them high and proud and just mill about in this area for me. Mill about in this area. Fantastic, fantastic. Just mill about. Okay, freeze for a second. Can I have a bit of space over here, please, so you can give some ribosomes some space? Now then, transfer RNAs are like the supplier. They supply the building blocks. The building blocks being the amino acids. Xena over here, okay, interprets the codes and builds them into the correct order. So, leaving this line clear here, can you go over there and just mill about until you require it? All right, Xena, who do you need first? And call them in for me, please.
GGA. Anita.
Glycine, where are you? Okay, in you come. Nita, just stand there, please, and hold it for me. Just give it to her. Thank you. Call the next one then, please. AUU.
AUU, which is over here. ILE.
ILE, coming in. Your time is up. In you come quickly. All right. Now, when they both come in, what happens is they form a very strong bond. So between you, could you link arms, please? So what we have there are 2 amino acids linked together. Okay, Xena, keep on going, please.
Val.
VAL, where are you? In you come, form a bond, please. Link arms, form a bond. Next.
GAG. Glue.
GLU, in you come, form a bond.
Okay.
That's fantastic. Right, can you go down, girls? Can you go down onto the floor so that Xena can see, please? That's fantastic. That's great. Keep going.
UGC. CYS.
Okay, and stop there. Can the rest of you tRNAs just sit down for a second, please? Fantastic. That's really, really, really good. Have a chocolate, guys. Have a chocolate. So what have we actually formed? What have we formed here? Femi, what have we formed? What have we got? What are these, did we say?
Oh, proteins.
Now, these are not proteins. These are
Amino acids.
amino acids. So what do we have here? Very good. I like that. We have a chain of amino acids. What do we get when we put a chain of amino acids together?
Proteins.
Fantastic. Now, the section of DNA we had up here was one small section of a gene. What we formed down here is one small section of a protein called one gene, one protein hypothesis. And it's very hard. Let's go through it again. So from the top, using the correct terminology this time. Francesca, what's the first thing we do? We go to the nucleus.
And copy a strand of mRNA.
Do we copy a strand of mRNA? We copy the strand of?
The DNA.
We copy a strand of DNA into
The mRNA.
mRNA. And do we use identical bases to the DNA?
No.
We use the
The
complementary. Excellent. So once we have the complementary bases in the mRNA, where do we take it to? Where do we take it to, Tony? Ribosome. Once it's at the ribosome, Xena, what happens next? These people called
what is it? Oh, transfer RNA.
What do?
They bring in their what was that word?
Amino
acids.
Fantastic. They bring in the amino acids and then they line them up. And what forms between each of the amino acids? What forms between them? Bonds to form a protein. And that is the one gene, one protein hypothesis. For a final time, because it is so hard. In the nucleus, the DNA is copied using the complementary base code. From this, we form messenger RNA, which goes to the ribosome. Transfer RNA molecules bring in what? Amino acids, which then bind to form a protein. Fantastic. This is vital, and your body is doing it at this very moment, millions of times over, all of your body. Does anybody know what we've actually formed there? We formed a chain. Have a look on the board. That's what you are. You form the first part of a very important protein. That protein is called insulin. And it's the thing that is helping you deal with those chocolates that I've just given you. Because without that, you would be in big, big trouble. Thank you very much.